Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to General class. This episode is Subelement G8, Question Group B, and I'm your host, Ron Call, KE7CR. This question set is about signals and emissions. So let's get started. The first question asks, which mixer input is varied or tuned to convert signals of different frequencies to an intermediate frequency? If you're watching the video, instead of just listening to the audio, you can see here a diagram of a superheterodyne receiver. This is where an RF signal is received, mixed with another frequency in a mixer to produce an intermediate frequency. Intermediate frequency is desirable because it's usually easier to filter. The signal that is mixed in the mixer to produce the intermediate frequency is called the local oscillator frequency. So that's the answer to this question, the local oscillator. The next question asks, what is the term for interference from a signal at twice the IF frequency from the desired signal? So the IF is the intermediate frequency. So what's the interference from a signal at twice the intermediate frequency? That's called an image response. The next question asks, what is another term for mixing of two RF signals? That's heterodyning. The terms heterodyne, mix, and modulate all mean to combine different frequency signals together. The next question asks, what is the stage in a VHF FM transmitter that generates a harmonic of a lower frequency signal to reach the desired operating frequency? So if you have a lower frequency and you want to take a harmonic of that, say twice that frequency or 3 times that frequency, that's called a multiplier. The next question asks, which intermodulation products are closest to the original signal frequencies? Intermodulation products are when any signals mix, you're going to get multiples of those frequencies. And the signals not only produce multiples like harmonics, say at twice the frequency or 3 times the frequency, but they also combine the frequencies in other ways. The frequencies also combine, producing the sum of the frequencies and the difference of the frequencies. They also produce intermodulation products or frequencies that are, for example, twice the frequency 2 minus frequency 1 and twice of frequency 1 minus frequency 2. So you get so many different intermodulation products, some of which you can filter out easily because they're far away from the original frequency that you're interested in. But others might be close to that frequency, and so then the filtering out of unwanted frequencies depends on the quality of the filter circuit. So the intermodulation products that are closest to the original frequencies are called odd order. If, for example, you have a second harmonic of frequency 1, so twice times frequency 1 minus frequency 2, the way to determine whether it's an odd order intermodulation product or an even order intermodulation product is to look at the exponents in front of the frequencies. So 2 minus 1 is an odd number, that's 1, so it's an odd order harmonic. 3 times frequency 1 minus 2 times frequency 2, 3 minus 2 is also 1, so that's an odd order harmonic. So in designing a filter, you would want to filter out any other frequencies other than the desired frequency. And it turns out odd order harmonics can be more difficult to filter out because they're closer to the original frequency that you want. The next question asks, what is the total bandwidth of an FM phone transmission having 5 kHz deviation and 3 kHz modulating frequency? There's a formula called Carson's bandwidth rule that says to figure out the bandwidth for FM, you take the frequency deviation added to the frequency modulation and then times it by 2. So if we take the frequency deviation, that's 5 kHz, add it to the frequency modulation of 3 kHz, that's 8 kHz, and then double it, we have 16 kHz. So that's the answer. The next question asks, what is the frequency deviation for a 12.21 MHz reactance modulated oscillator in a 5 kHz deviation, 146.52 MHz FM phone transmitter? So 416.7 Hz is the frequency deviation for the 12.21 MHz reactance modulated oscillator. So to calculate the frequency deviation, first you calculate the multiplication factor of the FM transmitter. So that's the transmitter frequency divided by the oscillator frequency. So that's 146.52 divided by 12.21. And the answer to that is 12. Next, you divide that transmitter deviation by the multiplication factor. So the deviation was 5 kilohertz. We divide that by the multiplication factor of 12, and you get 416.7 hertz. The next question asks, why is it important to know the duty cycle of the mode you're using when transmitting? The duty cycle is what percentage of the time you're actually transmitting versus in a receiving mode. So for example, for Morse code, there's a lot of spaces in between the dots and the dashes, the dits and the dahs. So you have downtime when the transmitter is not actually putting out power. For radio teletype, for example, it's at 100% duty cycle. It's always transmitting. The reason it's important to know the duty cycle of the mode you're using is if you're using a mode like RTTY, radio teletype, that's 100% duty cycle, it puts a lot more strain on your transmitter to provide that constant power output than if you're using a mode that has a lower duty cycle. For example, CW is probably around a 40% duty cycle. So the answer to this question is some modes have high duty cycles that could exceed the transmitter's average power rating. The next question, why is it good to match receiver bandwidth to the bandwidth of the operating mode? The filter circuits you use help to minimize any noise outside that frequency band that you're interested in. So you get the best signal to noise ratio if you can match your receiver bandwidth to the operating mode you're using. For example, CW, the bandwidth is around 150 hertz. So if you're using a 150 hertz filter, you're not going to hear as much noise outside that bandwidth. But a single sideband signal would use, say, a 3 kilohertz bandwidth. You need a much wider bandwidth just to receive the signal. So the answer to this question, it results in the best signal-to-noise ratio. The next question, what is the relationship between transmitted symbol rate and bandwidth? And the answer is higher symbol rates require wider bandwidth. You can send more information per second if you have a wider bandwidth in order to send more data streams. The next question, what combination of a mixer's local oscillator, or LO, and RF input frequencies is found in the output? And the answer is the sum and the difference frequencies. The next question, what process combines two signals in a non-linear circuit to produce unwanted spurious outputs? And that answer is intermodulation. Intermodulation is when you mix two signals together, two frequencies, and get unwanted frequencies as part of the outputs. The last question, which of the following is an odd order intermodulation product of frequencies F1 and F2? The answer choices are, A says 5 times F1 minus 3 times F2. But if you take 5 minus 3, the answer is 2. That's an even number, so it's an even order. Choice B says 3 times F1 minus F2. 3 minus 1 is also 2, so that's an even order. Choice C says 2 times frequency 1 minus frequency 2. 2 minus 1 is 1. That's an odd order. So the answer is C. Thank you for joining me for this question set, and look forward to seeing you in the next question set. 73, this is KE7CR.